Learning objectives. At the end of this topic, you will be able to define scientific conception of work, explain the concept of energy, describe rate of doing work. Introduction. Sheila was going to the movies with her mother. All living beings need food. Living beings have to perform several basic activities to survive. We call such activities life processes. The energy for these processes comes from food. We need energy for other activities like playing, singing, reading, writing, thinking, jumping, cycling and running. Activities that are strenuous require more energy.
I have read also that animals too get engaged in activities. For example, they may jump and run. They have to fight, move away from enemies, find food or find a safe place to live. Also, we engage some animals to lift weights, carry loads, pull carts or plow fields. All such activities require energy.
Right. Think of machines. List the machines that you have come across. What do they need for their working? Why do some engines require fuel like petrol and diesel? Why do living beings and machines need energy? We shall discuss about all these in this chapter. Work. Not much work in spite of working hard. There is a difference in the way we use the term work in day-to-day life and the way we use it in science. To make this point clear, let us consider a few examples. Rima is preparing for examinations. She spends a lot of time in studies. She reads books, draws diagrams, organizes her thoughts, collects question papers, attends classes, discusses problems with her friends and performs experiments. She expends a lot of energy on these activities. In common parlance, she is working hard. All this hard work may involve very little work if we go by the scientific definition of work. We work hard to push a huge rock. Let us say the rock does not move despite all the effort. However, we have not done any work on the rock as there is no displacement of the rock. You stand still for a few minutes with a heavy load on your head. You get tired. You've exerted yourself and have spent quite a bit of your energy. The way we understand the term work in science, work is not done. If we apply this scientific definition, these activities involve a lot of work. In day-to-day life, we consider any useful physical or mental labor as work. Activities like playing in a field, talking with friends, humming a tune, watching a movie, attending a function are sometimes not considered to be work. What constitutes work depends on the way we define it. We use and define the term work differently in science. Scientific conception of work. To understand the way we view work and define work from the point of view of science, let us consider some situations. Push a pebble lying on a surface. The pebble moves through a distance. We exerted a force on the pebble and the pebble got displaced. In this situation, work is done. A girl pulls a trolley and the trolley moves through a distance. The girl has exerted a force on the trolley and it is displaced. Therefore, work is done. A closer look at the above situations reveals that two conditions need to be satisfied for work to be done. A force should act on an object and the object must be displaced. If any one of the above conditions does not exist, work is not done. This is the way we view work in science. Work done by a constant force. To understand work definition in science, we shall first consider the case when the force is acting in the direction of displacement. Let A be a constant force. Let a constant force F act on an object. Let the object be displaced through a distance S in the direction of the force. Let W be the work done. We define work to be equal to the product of force and displacement. Work done is equal to force into displacement. W is equal to Fs. Thus, work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work is only magnitude and no direction. In equation W is equal to Fs if F is equal to 1n and S is equal to 1m, then the work done by the force will be 1 Nm. Here the unit of work is Newton meter, Nm, or joule, J. Thus, 1J is the amount of work done on an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. Energy. Life is impossible without energy. The demand for energy is ever increasing. The sun is the biggest natural source of energy to us. Many of our energy sources are derived from the sun. We can also get energy from the nuclei of atoms, the interior of the earth, and the tides. The word energy is very often used in our daily life, but in science, we give it a definite and precise meaning. Let us consider some examples. When a fast-moving cricket ball hits a stationary wicket, the wicket is thrown away. Similarly, an object when raised to a certain height gets the capability to do work. You must have seen when a raised hammer falls on a nail placed on a piece of wood, it drives the nail into the wood. We've also observed children winding a toy, and when the toy is placed on the floor, it starts moving. When a balloon is filled with air and we press it, we notice a change in its shape. As long as we press it gently, it can come back to its original shape when the force is withdrawn. However, if we press the balloon hard, it can even explode, producing a blasting sound. In all these examples, the objects acquire through different means the capability of doing work. An object having a capability to do work is said to possess energy. The object which does the work loses energy, and the object on which the work is done gains energy. An object that possesses energy can exert a force on another object. When this happens, energy is transferred from the former to the latter. The second object may move as it receives energy and therefore do some work. Thus, the first object had a capacity to do work. This implies that any object that possesses energy can do work. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is therefore the same as that of work, that is, joule, J. 1J is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule, kJ, is used. 1 kJ is equal to 1000 joules. Forms of energy. Kinetic energy. The various forms include mechanical energy, potential energy plus kinetic energy, heat energy, chemical energy, electrical energy, and light energy. Let's discuss about kinetic energy. A moving object can do work. An object moving faster can do more work than an identical object moving relatively slow. A moving bullet, blowing wind, a rotating wheel, a speeding stone can do work. The objects in motion possess energy. We call this energy kinetic energy. A falling coconut, a speeding car, a rolling stone, a flying aircraft, flowing water, blowing wind, a running athlete, etc. possess kinetic energy. In short, kinetic energy is the energy possessed by an object due to its motion. The kinetic energy of an object increases with its speed. By definition, we say kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Let us now express kinetic energy of an object in the form of an equation. Consider an object of mass, m, moving with a uniform velocity, u. Let it now be displaced through a distance s when a constant force F acts on it in the direction of its displacement. From equation 1, the work done W is Fs. The work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let a be the acceleration produced. We studied 3 equations of motion. The relation connecting the initial velocity u and final velocity v of an object moving with uniform acceleration a and the displacement s is v square minus u square is equal to 2as. This gives s is equal to v square minus u square divided by 2a, equation 2. We know F is equal to ma. Thus, using equation 2 in equation 1, we can write the work done by the force F as v square minus u square. W is equal to m a v square minus u square by 2a, or 1 by 2 mv square minus mu square. If the object is starting from its stationary position, that is, u is equal to 0, then 1 by 2 mv square. It is clear that the work done is equal to the change in the kinetic energy of an object. If u is equal to 0, work done will be 1 by 2 mu square. Thus, kinetic energy possessed by an object of mass m and moving with uniform velocity v is 1 by 2 mv square. Forms of energy. Potential energy. The energy transferred to an object is stored as potential energy if it is not used to cause a change in the velocity or speed of the object. We transfer energy when we stretch a rubber band. The energy transferred to the band is its potential energy. You do work while winding the key of a toy car. The energy transferred to the spring inside is stored as potential energy. The potential energy possessed by the object is the energy present in it by the virtue of its position or configuration. Forms of energy. Potential energy of an object at a height. An object increases its energy when raised through a height. This is because work is done on it against gravity while it is being raised. The energy present in such an object is the gravitational potential energy. The gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to the point against gravity. It is easy to arrive at an expression for gravitational potential energy of an object at a height. Consider an object of mass m. Let it be raised through a height h from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of the object mg. The object gains energy equal to the work done on it. Let the work done on the object against gravity be W. That is, work done W is equal to force into displacement, mg into h equal to mgh. Since work done on the object is equal to mgh, energy equal to mgh units is gained by the object. This is the potential energy EP of the object. EP is equal to mgh. It is useful to note that the work done by gravity depends on the difference in vertical heights of the initial and final positions of the object and not on the path along which the object has moved. Law of conservation of energy. We have learned that the form of energy can be changed from one form to another. Whenever energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation remains the same. The law of conservation of energy is valid in all situations and for all kinds of transformations. Consider a simple example. Let an object of mass m be made to fall freely from a height h. At the start, the potential energy is mgh and kinetic energy is 0. It is 0 because its velocity is 0. The total energy of the object is thus mgh. As it falls, its potential energy will change into kinetic energy. If v is the velocity of the object at a given instant, the kinetic energy would be 1 by 2 mv square. As the fall of the object continues, the potential energy would decrease while the kinetic energy would increase. When the object is about to reach the ground, h equal to 0, v will be the highest. Therefore, kinetic energy would be the largest and potential energy the least. However, the sum of the potential energy and kinetic energy of the object would be same at all points. That is, potential energy plus kinetic energy is equal to constant, or mgh plus half mv square equal to constant. The sum of kinetic energy and potential energy of an object is its total mechanical energy. We find that during the free fall of the object, the decrease in potential energy at any point in its path appears as an equal amount of increase in kinetic energy. There is thus a continual transformation of gravitational potential energy into kinetic energy. Rate of doing work. A stronger person may do a certain work in relatively lesser time. A more powerful vehicle would complete a journey in a shorter time than a less powerful one. The speed with which these vehicles change energy to do work is a basis for the classification. Power measures the speed of work done, that is, how fast or slow the work is done. Power is defined as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time t, then power is given by power is equal to work by time, or W is equal to P by T. The unit of power is watt, in honor of James Watt, 1736 to 1819, having the symbol W. 1 watt is the power of an agent which does work at the rate of 1 joule per second. We can also say that the power is 1 W when the rate of consumption of energy is 1 joule per second. 1 watt is equal to 1 joule per second, or 1 W is equal to 1 Js to the power minus 1. We express larger rates of energy transfer in kilowatts, kW. 1 kilowatt is equal to 1000 watts. 1 kW is equal to 1000 watts. 1 kW is equal to 1000 joules per second. The power of an agent may vary with time. This means that the agent may be doing work at different rates at different intervals of time. Therefore, the concept of average power is useful. We obtain average power by dividing the total energy consumed by the total time taken. Commercial unit of energy. The unit joule is too small and hence is inconvenient to express large quantities of energy. We use a bigger unit of energy called kilowatt hour, kWh. Let us say we have a machine that uses 1000 joules of energy every second. If this machine is used continuously for 1 hour, it will consume 1 kWh of energy. Thus, 1 kWh is energy used in 1 hour at the rate of 1000 joules per second, or 1 kW. 1 kWh is equal to 1 kW into 1 h. That's equal to 1000 W into 3600 S. That's equal to 3,60,000 joules. 1 kWh is equal to 3.6 megajoules, or 3.6 into 10 to the power of 6 joules. The energy used in households, industries, and commercial establishments are usually expressed in kilowatt hour. Summary. Let's summarize the topic. Work has only magnitude and no direction. Energy is transferred from the former to another. The kinetic energy possessed by an object of mass m moving with uniform velocity v is half mv squared. The gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to that point against gravity.